Hello, I'm Jay. Today I'll introduce our recent NeurIPS 2021 paper, QVHighlights Detecting Moments and Highlights in Videos while Natural Language Queries. My collaborators are Tamar and Mohit. We're from UNC Chapel Hill. Internet videos are growing at an unprecedented rate. In the top left, we show the hours of videos uploaded to YouTube every minute in the last few years. As we can see, it is growing very fast. Enabling users to efficiently search and browse those massive collections of videos is essential for improving user experience of online video platforms. When users search a specific text query, it is desired that the system could return the most relevant moments and highlights to the query. Here we show an example from our QVHighlights dataset, where each example has a natural language query and a video. For each query, it is also paired with a single or multiple moments inside the video that is most relevant to the query. For each clip inside the annotated moments, we annotate through highlightiness or saliency scores from different annotators. Those scores ranging from very good to very bad, suggesting whether this clip is silent or not with respect to the query. For data collection, we start with collecting videos from YouTube. We first create a list of queries such as travel vlog, daily vlog, and news. We then search those queries on YouTube and download the top videos for each query. Next, we filter the videos based on the set of criteria such as language and the duration. Those videos are split into 2.5 minutes long short videos, and next we use I'm the Mechanic Turk for annotation. For I'm the Mechanic Turk, we present the annotators one of our collected videos. Given this video, for example, the first step is to watch the video and then write a query that is relevant to the video content. And for this example, the writing query is a shark is swimming underwater. And the next step is annotating all the moments that are relevant to the writing query. It can be a single moment or multiple moments, depending on the video and the query. In this example, there is only a single moment that corresponds to this query, as we indicate by the dashed red box. After we get the relevant moments, we next ask 3 different users to rate each clip inside the annotated moments. Specifically, we ask the question, is the clip good as a cover or highlight for the video? And the scores are collected in a Likert scale style, where we have 5 scores from very good to very bad. A rating of very good meaning the clip is relevant, eye-catching, and the object and the event of interest is clearly visible. And in contrast, a rating of very bad meaning the clip is irrelevant to the query. In this example clip, as shown in the bottom left, all 3 users rated it as good. After this procedure, we collected 4 QVHighlights example, consisting of a natural language query, a video with associated moments, and the clip-wise saliency scores. And here we show a comparison with existing moment retrieval and highlight detection datasets. And we see that from this figure that QVHighlights is the only dataset that supports both moment retrieval and highlight detection tasks. And it is also the only dataset that has more than 1 moment per query for each video. And it is the largest dataset for query-based highlight detection. Here we show the top unique verbs and nouns in the collected queries in each video category. We notice queries in different video categories typically have different unique words. For example, in daily vlog, there are more actions and objects about daily activities, such as cook and clean. While for travel vlog, there are more words related to travel, like swim and visit. We also studied the distribution of moment lengths in the top and normalized the moment center in the bottom. On the top, we notice our dataset has a rich variety of moments that vary greatly in length. Around 38% of the moments have a length of equal or less than 10 seconds, while around 23% are more than 30 seconds. And on the bottom, we see the moments distributed almost equally along the videos, indicating that our dataset does not suffer from the temporal biases that is commonly seen in other datasets. And here the temporal bias means that more moments appear in the beginning of the video. Given the QVHighlights dataset, we define the task as follows. The task input is a video along with a natural language query, and we expect the system to locate moments that are relevant to this query, as well as predicting salience scores for each clip in the video. For this task, we proposed a novel Moment-DETR model. The architecture is conceptually simple with a transformer encoder-decoder architecture and the 3 added prediction heads for predicting salience scores, 4 at background classification scores, and also the moment coordinates. We use an OpenAI clip text encoder along with a 2-layer multi-layer perceptron to encode the text queries into a sequence of embedding vectors. And for video, we use 2 different encoders, an OpenAI clip image encoder and a slow-fast video encoder. We extract video features every 2 seconds from those 2 encoders, and then concatenate them together after further processing using a 2-layer multi-layer perceptron. We get a sequence of video embedding vectors. We next concatenate the text and the video sequences along the sequence dimension as a single embedding sequence and forward it into our transformer encoder. After the input text representations are encoded by the transformer encoder, we build a salience score prediction head on top of the resulting representations. Specifically, we use a linear layer to predict the salience score for each video clip. We then apply a hinge loss on the predicted clip-wise salience scores, where we encourage the clips that have higher user ratings to be better than the clips with lower ratings. And we also encourage the clips within the moments to have higher scores than those outside. And we combine those 2 objectives together as our final salience loss. We also added a classification head for 4-way background classification, which is optimized using a cross-entropy loss. And for moments, we use another head that predicts the moment width and the center coordinates. This is optimized using an L1 loss and a generalized IOU loss. As Moment-DETR uses transform architecture, which often needs a large amount of data for training, while the annotated data is quite expensive. Thus, in this work, we also consider using automatic speech recognition ASR captions for weakly supervised pre-training. Specifically, we use the ASR caption sentences and their associated timestamps as a query moment pair for training. For example, you see that in this clip, the first caption sentences, you've got it like a bookcase on their side. As you can see here, there's a correspondence between the ASR caption content and the video content, which can be leveraged by the model to train the parameters. We split the collected data into 70% training, 50% validation, and 50% testing. And for moment retrieval evaluation, we use mean average per session and require different IOU thresholds. And for highlight detection, we set the clips with a very good rating as positive. And then we use MAP and hit at 1 to evaluate the performance, where hit at 1, meaning with the clip with the high salience score is positive. And here we compare Moment-DETR with state-of-the-art methods on both tasks. And we see that firstly, Moment-DETR has better overall performance on both tasks. And then secondly, we notice our weakly supervised pre-training strategy gives a significantly performance gain over the model that is trained from scratch. In this table, we show the impact of losses by turning off one of the losses at a time. When turning off the salience loss, we observe a significant performance drop for the highlight detection task, and surprisingly, moment retrieval task as well. We hypothesized that the moment span prediction losses L1 and the GIOU loss and the classification loss, they do not provide strong supervision for learning the similarity between the input text query and their relevant clips, while the salience loss gives a direct signal to learn such similarities. When turning off one of the span prediction losses, the L1 loss and the IOU loss, we see a notable performance drop in moment retrieval task, while the high detection performance stays similar, showing that both losses are important for moment retrieval task. To better understand the role of pre-training, we examine the effect of using data of different domains and sizes for pre-training. Specifically, we use how to 100 million instructional videos of different sizes for pre-training the Moment-DETR model. And then we evaluate its fine-tuning performance on our QVHighlights dataset. We noticed that this out-of-domain pre-training also improves the model performance, even when only trained on 2,500 videos. And when increasing the number of videos, we see there is a steady performance gain for the moment retrieval task. Compared to in-domain and out-of-domain videos, we noticed that 5,400 in-domain QVHighlights videos greatly outperforms 10,000 how to 100 million videos, demonstrating the importance of aligning the pre-training domain and the downstream task domain. In this table, we show Moment-DETR's performance on another moment retrieval dataset, Charades-STA, and we notice that Moment-DETR shows a significant performance gain on R1 at 0.5. After pre-trained on 10,000 how to 100 million videos, Moment-DETR's performance is greatly improved, setting new state-of-the-art for the dataset. This shows Moment-DETR's potential to adapt to different data and tasks. We visualize moment span predictions for all the 1,550 QVHighlights validation videos for the 10-moment query slots in the Moment-DETR decoder. And for this figure, the x-axis means the normalized moment span center coordinates with respect to the videos, while the y-axis shows the normalized moment span lengths. And in this figure, we say that each slot learns to predict moments of different patterns, that is, different temporal locations and different delays. And for example, the second and fourth slots learn to predict shorter moments near the end of the video, while the fifth and the sixth slots learn to predict both short and long moments near the center. Here is a correct prediction of our model. We can say that the model is able to correctly localize to disjointed moments relevant to the user query. Meanwhile, the saliency scores also align very well with the ground truth score curve. And not surprisingly, this saliency score curve also matches with the moment predictions, where we see higher scores for localized regions than those outside. Here we show a failure case, where the model incorrectly localized a partially true moment, which is the second frame in this video, where the family is playing on the court but not playing basketball. Our data and code is publicly available. Thank you for your attention.